we have been looking at coupler curves. So, if you look at the 4 bar and you try to write the equation of the coordinates of a coupler point, you will find that it is a 6th order equation, and that is the reason you can. So, if I write the, I can get the coordinates x and y if I eliminate. So, write the equation of the curve, okay, of the locus of point P by eliminating, say, the input angle from the equation in terms of the link lengths. If I write that, I will get a 6th order curve, which kind of explains why you get such complex curves. So, last class we looked at, we were looking at the concept of the cusp, right. So, you have multiple points in the coupler curve where, multiple point is a point where the tangent is not uniquely defined, okay. So, a multiple point is a point on a curve for which the tangent is not uniquely defined. So, in the case of the cusp, for instance, if you look at this as the curve, then you have this tangent T for this curve as well as for this curve. The curves are coincident. In the case of a cusp, the two tangents are coincident, okay. So, these are a cusp and a crew node. The crew node is that figure 8 that we saw. So, if the coupler curve has a point like this, then again the tangent is not uniquely defined, because at this particular point you could have a tangent like this or a tangent like this, okay. So, these are called double points, cusp and crew node. In the case of the cusp, the two tangents are coincident. Whereas, in the case of the crew node, which is also double point, so at which the curve crosses itself. So, a crew node is a double point where the curve crosses itself and there are two tangents at this point. So, the curve has two tangents at this double point. So, the cusp is formed. We looked at the concept of fixed and moving centroids in the last class, and you saw that the motion of the 4 bar can be, or the motion of the coupler relative to the fixed link can be replicated, by the same motion as the moving centroid rolling on the fixed centroid. And a cusp is formed. So, this is another, I will show you this. So, this is another case. The green one is the moving centroid rolling on the blue fixed centroid. Okay. So, if you choose points on the moving centroid, okay, from that it follows that as you saw with the rolling disc, right, where it contacts the fixed centroid, where the point on the moving centroid contacts the fixed centroid, you have a cusp. Okay. So, that is, so in this case for instance, you have, so this is my in position 1, this is my instant center C1. Okay. The coupler point that I have chosen, okay, is contacting the fixed centroid because it is the instant center at that point. The moving centroid, when it contacts the fixed centroid, that point is the instant center, right. So, here for position 1 you see that is the instant center, and you see that there is a cusp in the path of the coupler point. Okay. These will hit at different other points, okay, because at any instant there is only one contact between the moving centroid and the fixed centroid. These are other possibilities. So, points D, E, F also lie on the moving centroid, but they are going to contact the fixed centroid at other rotations of the crank. Okay. And here it probably indicates, so you have the numbers indicate when a particular point contacts the fixed centroid or when that is the instant center. Okay. So, at the instant, that is the if E is the instant center at some rotation of the crank, then there is a cusp that is formed in the coupler curve of E. So, if a coupler point lies on the moving centroid, then a cusp will form at the point where the point and the instant center are coincident. In other words, when the point contacts the fixed centroid. A cusp will form when a point on the moving centroid contacts the fixed centroid. Okay. The case of the crew node.
Can you go back? Those other curves, those are coupler curves.
Those are also those are coupler curves for these points. So, F is a point on the coupler. Okay. So, F will trace this curve.
So, significance of cusp is?
Significance of cusp is the point, the coupler point comes in a particular direction, its velocity goes to 0 and it reverses direction without any shock. So, if you want to do a pick and place operation, okay, you want to play, you locate it at the cusp, okay. So, it will place it and smoothly retract. Okay. So, there is no shock due to the velocity, the change in the direction of the velocity.
There should be two cusps in the coupler curve for pick and place kind of.
Yeah, it depends. So, yeah, like for instance, you could have this kind of a curve, no? Or you could have some other point having a cusp for, yeah. So, this would be, so you could pick one place and drop it at some other place, for instance. This would be okay, or it could just be a pick operation. So, something is there, it picks it, it approaches it, picks it up, takes it, or just a place operation, drops it. Okay. So, it is very, even for that film strip, right, it pulls it down, then neatly retracts. Okay, it is just able to neatly retract, change the direction and come out of the hole in the film strip example that we looked at. So, that is the advantage of the cusp. Reversal, you get cusps provide for reversal of motion without impact or shock. So, they are very useful in mechanisms for that reason. Again, for that you would have to actually look at the whole curve in order to be able to, if that is the objective of your design, then that is something where you look at the nature of the coupler curve itself rather than just precision points. Okay. Here we are looking at, and you can use the atlas to find curves that have a cusp and find coupler points that will have a cusp at a particular location.
Like for a coupler curve, there can never be more than one.
Why not? It will just contact the fixed centroid at a different, if you have like this one, right.
Asking for a given coupler curve, so can it be two cusps?
Yeah. So, if you look at let us see, I do not know if I have, you can have a coupler curve that is shaped like this, for instance, right. So, this is a cusp, this is also almost a cusp, these are also it's so you could have, so this is probably not a very good example, but there are some where it is sharp on both sides, you have a cusp on both sides. So, it is possible.
But what does that mean from the moving
So, here no, this one does not. I am trying to see if there is one that I can show you. So, here for example, this could be, so in terms of a perfect cusp, because it means your two instant centers will coincide. It happens only at one. So, you will have a so a pure cusp you could probably have only at one location in the coupler curve. Yeah. Okay. It's a good question. Yeah. So, yeah.
Seeing a coupler curve, we cannot tell a point's actual cusp or not.
You can, because a sharp, that is your cusp, right, where the point comes and there is reversal in direction. So, that is why this may be close, but may not. So, it really depends on. So, here also for instance, now there it just enters, right. In the case of the film strip, you only have, yeah, you are only using the lower portion as the cusp. So, no, yeah, you are only using one. So, a pure cusp in terms of the definition, yeah, there should be only one for a coupler curve.
Your curve is intersecting.
It is intersecting here, so that means it is contacting it,
but at two different instances.
At two different instances.
So,
So, it is possible. Then see, if you look at this one here, you have the point. So, you have say a coupler point on the move. See, the question is whether the same point will contact the fixed centroid multiple times, which may not happen, because you could have multiple points on the centroid which will generate cusps, right, but is the same point going to contact the fixed centroid?
Or for one particular rotation, it will start at a point and
It will start at a point and come back to that.
It can never.
Yeah.
Same point can never.
So, the same point will not, because it is, yeah. So, the same point, so you can only have one cusp in the, but you can have something close to that, but probably not in the strictest definition of the cusp, you can only have one cusp in the curve, coupler curve, okay. Because if you pick one point on the moving centroid, it is going to contact the fixed centroid at only one other. Is it possible for it to contact it? That's, I'll just double check that just in case. Okay, all right.
In that example, you had the free pivot, like moving centroid. Green is the moving centroid, right?
Yeah.
And that has
Point on the moving centroid contacting the fixed centroid at multiple places. Point, yeah, that is what is happening here, no?
So the cusp definition is coupler curve intersecting with
Yeah,
moving centroid.
correct. When it, yeah. Nobody has asked me this question before, okay. Yeah. So, here it is that same point, if you look at that,
Red curve.
the green curve, the red, that shows the velocity. So, you can see here that it yeah, again goes to 0, and so for the same point, I guess it's, I'll have to look at that, I'll have to look at that too. That is a good question. Okay. So, in this one it appears that you can have,
But in this case, where it's intersecting is just the, it just moves in a circular arc, right?
it does not have to move,
No,
it has to roll at that point, no?
the point on the coupler is just the link, the joint itself, right?
Yeah.
So that anyway moves in an arc when you.
So, is that the point on the moving centroid? See, if you look here, it's if you look at this area here, you can actually see some overlap in the two greens. They are not identical, they are not one on top of the other.
That is the point on the rocker itself.
This is a point on the rocker, yes, and it is,
When we plot the rocker's curve, it is moving, like it is changing.
yeah, that is the magenta.
Will it be also considered a coupler curve? The point.
So, that is basically a special point on the coupler, right, because it is,
Only.
yeah, it only moves along the circular arc. Yeah, that point actually reverses direction, because at the limit positions. So, if you consider that as a point on the coupler, that is reversing direction.
Then all the rockers will have to.
All the rockers will have, but we do not really consider that as a, because it's the degenerate case, you only get a circular arc, right. So, the circular arc is basically like something with a double cusp, kind of collapsed. That's essentially what the circular arc is. So, maybe that is the only, so true coupler point, okay, so something that is not on the input or the output link, on the crank or the follower, will probably have only one cusp, okay. Okay. But I need to do some reading on that to see if, but these 2 points, yeah, because you do have reversal of motion, even with the crank rocker, if you look at it, you have it goes to, velocity goes to 0, then it reverses. So, that is what this in this case the coincident points are, but we do not really treat those two pivots as coupler points, because you are not going to get anything more interesting than a circular arc. Okay. So, a crew node, to locate crew nodes, so these are like your figure 8 double points where it comes to that point and then follows a different path. So, it reaches that point twice, but follows different paths each time. Okay. So, let us look at where we can locate a crew node on the coupler curve. So, suppose these are two positions. I have two positions of the crank here, OA A1 and OA A2, and let us say the coupler point M is at this Q both times. Okay. So, that means it is reaching Q with two different input angles essentially. So, two different configurations of the linkage give rise to the same location for that coupler point. Okay. So, these are two positions of coupler base A1 B1 and A2 B2 for which the coupler point assumes the same position Q. Okay. So, now consider the quadrilateral OA A Q A2. OA A1 Q A2, quadrilateral OA A1 Q A2, right here. So, here you know OA A1 equals OA A2, then A1Q, which is the A1Q equals A2Q, and side OA M is common, OAQ is common, right. If you, therefore, this is the OAQ is the bisector of that angle. To beta. Okay. So, similarly, if I look at OBQ, that is the bisector of angle B1 Q B2, okay, which I call 2 gamma. Okay. But my coupler A1 B1 M ABM is rigid. Okay. Therefore, what does it, I can just call it ABM. Therefore, this angle 2 beta plus alpha equals 2 gamma plus alpha. This is the common, this is 2 beta. So, if I look at A1, because angle A1 M B1 equal to M B2. Therefore, beta equals gamma. Angle, if I look at this, if I look at angle OA QOB, okay, that angle equals beta plus alpha plus gamma. Yes? Okay. And if I look at the vertex angle of the coupler, because beta equal to gamma, that is angle A1 M B1, I can also write that as alpha plus beta plus gamma, because beta and gamma are equal. I just showed that beta and gamma are equal, therefore, that is also equal to this thing. So, this implies, if I consider, so that means this angle OAMOB, this angle is the same as A1M B1 or A2M B2, whatever, okay, the coupler angle, vertex angle at the point M. So, OAQOB equals A1QB1 equals A2QB2 angles, right, that is what I. Now, if I draw a circle, okay, so I construct a triangle such that this angle, okay. So, if I construct, if I have a circle where this is the angle subtended at the circumference, then I can pick any point there and it will have the same angle, right. This chord OAOB will subtend the same angle at any point on the circumference of this circle. That means, I can pick my point Q anywhere on this circle. So, this circle, if construct a triangle, OA, OC, OB, which is similar to the point triangle ABM. With OAOB as the base. Then, if I take any point Q, that angle is going to be the same as this angle subtended here. Okay. So, Q must belong to this circle. Q must lie on the circle passing through OA, OB and OC. The point Q that I choose, the point Q where the crew node happens will lie on the circle that is formed by OA, OB and OC. This circle is called the circle of foci. It has some other significance, but we will not. So, point Q must necessarily belong to the circle passing through points OA, OB and OC. So, where the coupler curve intersects the circle of foci, you will have a double point. Okay. A double point exists at the intersection of the coupler curve with the circle of foci, circle of singular foci. It is actually called circle of singular foci. And the circle of singular foci is essentially the circle passing through something that has the same. So, if I have a coupler, if this is my coupler, it is similar to it is a triangle that is similar to the coupler triangle.
So basically how we construct the circle is by finding a singular point in which we have a chronode and then finding other chronodes. Like we need
Yeah.
a point M, Q where at
You
least
need a
one-
point M, okay, and if you want it, so where that point M may have a double point is, so you have the point M, okay, you construct the circle of foci with OA, OB as base and similar to A1 M B1, okay. So, if the coupler curve of that point M intersects this circle, you will have a crew node at that point. Okay, so, here M and Q are coinciding at this, two. So, Q is a point on the plane, okay. M is a point on the coupler. So, you choose a coupler triangle, the point M will have a crew node if its coupler curve intersects this circle of singular foci. So, now let us look at the synthesis. So, you can generate coupler curves that are symmetrical about an axis, okay, and there is a fairly simple construction that can give you a symmetrical coupler curve. Okay. So, then again, if you want to generate something that has two cusps, we have to see that again, it is an interesting come back to that. Okay. So, let us look at how we would generate, how we would design a linkage to generate a symmetrical coupler curve. Okay. So, the condition for that is coupler curves with an axis of symmetry may be generated by a 4 bar with a coupler base AB that is your L3 in your and a follower of equal length. So, here I am saying AB equals OBB. Okay. This is a sufficient condition, but not a necessary one. So, there may be other linkages that can generate a symmetrical coupler curve. This is one way to generate a symmetrical coupler curve. Okay. It is not necessary that this condition has to be met in order to generate a symmetrical coupler curve. Okay. Then the coupler point generating a symmetrical curve must then lie anywhere on the circle centered at B and passing through what this says is, if this equal to this, okay, then if I create M such that it lies on a circle that is centered at B and passes through OB and A, then that all those points M will generate symmetrical coupler curves. So, let us look at why that is the case. So, if you look here, if you look at this coupler triangle ABM, okay, this angle B cap, okay, if this is the angle B cap, then AM, so this is the angle that AM, the chord AM subtends at the center of the circle B, okay. That means AM subtends the angle B cap by 2 at OB, right, okay. Okay. So, we have established that this angle is B cap by 2. Okay. So, now let us look at, so in the previous case, if you see here, BOB equals BA, therefore, the circle passes through OB also, right, okay, equal is equal to this equal to BM. So, those three are equal. So, let M be such a coupler point and we want to show here that, let us take the crank OA to lie in symmetrical positions about the frame, okay, OA, OB is here. Let us say for position 1, M1 is where the coupler point is, okay, and let us say that for this position OA, A2, when it is reflected about the, for that crank position, M2 is the point. You want to show that C is basically the perpendicular bisector of M1, M2, because then that will establish it and that it makes a constant angle to the frame. if you can show that, then it implies that it is a line of symmetry, it does not change. Okay. So, for all positions of the crank on either side of the fixed link, you will find a corresponding, you will find that M is reflected about this line of symmetry. Okay. So, you get a symmetrical coupler curve. Okay. I have the linkage in these two positions, OA A1 B1 OB and OA A2 B2 OB. Okay. These are the two positions of the linkage. Now, I want to show that, okay, let us consider this triangle. May first show that AM A1 equal to OB A2, okay, OB M1 equal to M. Okay. Let me consider triangle OBB in this case, if I consider these two triangles OA A1 OB and OA A2 OB, I am taking these symmetrical about OA OB. This is the common side, OA A1 equal to OA. So, these two triangles are congruent. Okay. Therefore, OB A1 equals OB A2. Okay. So, OB A1 equals OB A2. Now, let me take triangles OB A1 M1, is that, and OB A2 M2. That will give me, I want to show OB M1 equal to, or should I take OB A1 B1, okay, OB A1 B1 and OB A2 B2. Okay. Okay, first I considered, okay, let me first do it systematically. I look at triangle OA A1 AB is congruent to triangle OA A2 OB. Therefore, I have OB A1 equal to OB A2. So, these are two positions, A1 A2 are symmetrical. Okay, I am considering the linkage because that is important. Consider the linkage in two positions OA A1 B1 OB and OA A2 B2 OB, for which points A1 and A2 are symmetrical about the fixed link OA OB. Now, if I look at triangle OB A1 B1, OB A1 B1 and triangle OB A2 B2. Okay. Now, A1 B1 equals A2 B2. So, same coupler base, right. Then OBB1 equals OBB2, follower, okay, and I have shown that OBA2 equals OBA1 because the corresponding sides are equal. So, by SSS I have triangle OBA1B1 is congruent to triangle OBA2B2. Okay. Now, consider the triangle OBB1 M1 and OBB1 sorry OBB2 M2. OBB1 M1 and OBB2 M2. Yes?
Now you can directly say that you are rotating it, right? Because OB A2 and
Yeah.
B2 is a
Yeah.
rigid body.
Yeah. This is a rigid body and you are rotating it about this. So, that means this we already know is this angle, therefore, beta 1 equals beta 2 from these two, right. Because again the three sides are equal, beta 1 equals beta 2. Beta 1 equals beta 2 I say from this itself, OA A1, where is it, OB A1 B1, I have shown these two are equal, right. OB A1 B1, OB A2 B2, those two are equal, therefore, corresponding sides of congruent triangles, therefore, beta 1 equal to beta 2. Okay. So, using that, because this is B plus beta 2, this is B plus beta 1, I show that from these two triangles, from congruence of these two triangles, I have OB M1 equal to OB M2. Okay. Now, let us look at these angles. Okay. I have this line C, okay, which makes some angle gamma with respect to the frame. Okay. So, I have, if I look at this triangle, I have shown that OB M2 B2 is congruent to OB M1 B1, right. So, I have this angle delta plus gamma, this, okay, this is delta, this is gamma, this is equal to alpha plus B cap by 2. Because this is now an isosceles triangle, OB M1 M2, okay. OB M1 M2 is an isosceles triangle. Therefore, these two angles, it bisects that. Okay. So, I have delta plus gamma equals alpha plus B cap by 2. Then from the other one I have, from, because these two are equal, I already showed that these two angles are equal, I have B cap by 2 plus this one alpha plus gamma, this angle, okay, equals delta plus B cap by 2, okay, from these two triangles. This is from OA, A1, OB and OA, A to OB. Okay. If I add these two equations, I get rid of alpha and delta. Therefore, I get 2 gamma equals B cap or gamma equals B cap by 2. B cap is a constant angle. It is not an angle that is varying with time, because B cap basically locates the point M with respect to the coupler base. Okay. Since this is the rigid body, this angle is constant. B cap is a constant angle. Therefore, the angle that this perpendicular bisector makes with the frame does not change, which implies that M1 and M2 will always be equidistant from this. So, this becomes the line of symmetry. C becomes the line of symmetry for this coupler point M1. Okay. So, the construction of, so to find a coupler point with say a certain line of symmetry, okay, say I want a line of symmetry at a certain angle to the base, I would take the follower length to be equal to the coupler base, okay, draw a circle that passes through, that is centered at B and passes through OB and A1, okay, and then choose that angle as twice the angle. So, I would locate the point M1 on the circle such that it makes twice the angle as the angle of symmetry, as the line of symmetry. So, here this is B cap by 2, that is what I have shown. Okay. So, this is one way of constructing a symmetrical coupler curve.